In the last lecture, we talked about monadic image processing, and that's where we take a pixel from the input image, apply a function to it, and put the result into the corresponding pixel in the output image. And we looked at a number of functions. We looked at gamma encoding and decoding, we looked at thresholding, and so on. So it's the same function is applied to every single pixel in the image. What happens here is that every output pixel is a function of the pixels in a square region around the corresponding point in the input image. So the input to the function is a number of pixels, the output is a single pixel value. So such a function, which is based on a number of pixels, can then say something about either the uniformity or the variation of the pixels over that input square region. We call this a window and denoted by the symbol W. So let's consider an example function that we might use, and a common one would be to consider the average. So what we're going to do is for that square input window, take all of the pixel values, compute the average, and place the average into the corresponding pixel in the output image. So here's the original image, the Mona Lisa image that we've seen before, and the output is the average pixel value over a 7 by 7 window. So what the average can do is it can reduce noise, but we also see that it reduces the resolution. It's made this image look somewhat blurry. Let's see how this actually works in practice. And I've constructed a toy example here where we have an input grayscale image, double precision input image. So the pixel values vary between 0 and 1. So we have a grey background with values of 0.3 and a bright square in the middle where the pixel values are 0.8. We'll start the animation, and what we can see here is the input pixel window, which is shown here as red, and see it moving, marching across the image, left to right, top to bottom. And what you can see on the right hand side are the average values being deposited into the output image. A couple of things to note. First of all, note that we can't compute the pixel values in the outermost row and column of pixels, and we'll talk about that shortly. Also note that the quite clearly obvious bright square in the input image has been smeared out. That value of 0.8 only exists now at a single pixel in the output image. Around that are some slightly brighter values, and beyond that is the background. So we see here what we saw when we took the average of the Mona Lisa image, that the sharp, crisp boundaries in the image have been smeared out or blurred. Now the effect of the window size makes a real difference. So again, here is our input image, and if we compute the average with a 7 by 7 window moving over the input image, this is the result. And if we increase the size of the window, now it's a 21 by 21 window, we can see that it is very, very blurry indeed. So what tends to happen is that any feature in the image that's smaller than the size of the window will be very strongly attenuated. It will tend to disappear in the output image. We might say that the output image is blurry, fuzzy, has a lower resolution, or whatever. We have blurred out, smoothed over, fine detail in the image. Let's try this on a full-scale image. We're going to load our favorite image, the Mona Lisa, into the workspace variable im. I'm going to compute a new image in the workspace variable, which I'm going to call S7. And every output pixel is the average of a 7 by 7 neighborhood or window of the pixels in the input image. To do that, I'm going to use the toolbox function icon, and we'll explain about this function a bit more as we proceed. The first argument is the image that I'm going to perform the average on, which is the Mona Lisa image in the workspace variable im. And the second argument defines the area over which we compute the average. Now, I wanted to compute the average over a 7 by 7 window, and so to specify that, I pass in a matrix with the function 1's 7, 7. That produces a matrix that's 7 by 7, and every element in that matrix is 1. So that second argument defines the region over which I'm going to perform the average for every single input pixel. And we're going to display the original Mona Lisa image and going to create another figure and to display the averaged version of that. And we can see that there is a lot less detail in the background. It's much smoother. You might say it's blurrier. You might say it has got lower resolution. Now let's increase the size of the region over which we're doing the averaging. So I am going now to correlate with a window which is 21 by 21 pixels in size. And I'm going to display that image, and we can see that this looks very, very blurry indeed. The effect of averaging over a region of pixels is to eliminate very fine detail within the image. So any detail that's of a size that's smaller than the window that we're using, in this last case 21 by 21 pixels, any detail that's of the order of 1 or 2 pixels in size is going to be eliminated.